Let's create a model for a piezo-resistive based pressure sensing device. Let's create the model in the 2D form and then we'll convert it to 3D and then we'll do the analysis part of it. Okay. So here I define 4 layers. Layer 1, TRI, metal, piezo, and fourth layer is via. Let's change its color. You can choose any color of your choice. There's no restriction. Click OK. So we have 4 layers and this is the order of the layer. So it starts from 0. This is the order of the layer. Okay. Let's create the first rectangle here. Ping DRI. So I select the first rectangle. Select this. In case if the panel here is not visible, then you have to enable this by selecting this option, command line. Then you get this command window. So I select a rectangle and then enter these coordinates: -200, -200, 200, comma 200. Okay. So let's position the piezo resistive layers. Go to piezo, then select rectangle and then enter these coordinates. 4 rectangles is what I'm trying to create. Another rectangle. So we have 4 rectangles and 4 different positions. Then let's create via hole buttons. We go to via, then here let's create a via contact and 4 different piezo resistors. So here we select the via. So I'll go to one of the piezo resistor and then select a rectangle. I can also draw a rectangle in this fashion. So here each dot what you see is of distance 1 micrometer by 1 micrometer. It is shown here. So here I select a rectangle and using the left button of the mouse, I hold the button, I select 5 micrometers, 1, 2, 3, 4, 5 and drag it down. So it is of the dimension 5 micrometer by 10 micrometer square. Click and leave the button. And similarly, I add one more via contact in this fashion. So 2 positions I have done it. Now I'll show you how to take the mirror option. So since this via is selected, we can select these two via, and then you can take the mirror option. So here mirror option is the mirror line where we can select on the specific uh, center origin. So drag a center line, then leave. You can see that via contacts are generated on the other side also. So you can press escape button to deselect that. So on the either on the other side also we have the via contacts. Okay, let's create it here. 1, 2, 3, 4, 5. Drag down. So I select these two buttons now, and then select the mirror line. Click on the origin point, drag horizontally this time, exactly straight, and then click leave the button. So you can see the mirror option has given us another two via contacts on the other side. So I press escape again. So you can either retain full or in the outline form, whichever is comfortable to you. So these coordinates, whatever we are entering, are the coordinates here, and this is the center point, origin 0, 0. Keeping this in mind, we keep entering the coordinates. Now let's create the contacts. So -50. So finally, I end up creating this geometry. Okay, so let's save this file. Once the layout is created, let's define the process flow using this module called IntelliFab. In IntelliFab, we have two panels. One is on the left side, the material library. On the right side, we have the process simulation area. So we go to the material database and then start defining. So let's define silicon. By default, it is 100. You can change the orientation here if required. So let's retain 100 itself. Every time we want to add a new process, we can go to that specific material. Either we want to do deposition, or that we want to do etching, we want to do lithography. So we can select that particular option and double click on that. So here I already have the process definition done. Let me open it directly. Let me explain it to you each step by step how it was done. Okay, I've already created the process. Let's get to the specifics of the process. So here I have opened the process file, and then I'll set this value. I'll initialize this file, selected, initialized it, and then by default this is set. Okay, so you retain this value as it is as of now, no change. Whatever the value that comes on your PC, let it be as it is. It need not be changed. Okay, I click OK. Now I have selected SI100 orientation silicon. How much is the thickness? Thickness is about 50 micrometer, that is 50,000 nanometer. And above that, I deposited a PR material, photoresistive material. So here in deposition, you can see that material is there. Spin, double click on 001. So this process gets added here. Above that, I have done the exposure, that is in lithography. I go to exposure, UV, contact and sus. So you can see contact and sus. Here, once we define the process simulation, and when we are trying to do the lithography process, here we have initialized a mask file. So software will read how many layers are there in that file. And here in this case, we have 4 different layers. Including 0, it is 5, but for our concentration is on the 4 layers. This 4 layers, which layer should come at this place? So here we require a piezo layer. We are trying to embed a piezo material. So here we select piezo layer. Okay. Here, as you see it, the process and the process ID needs to get selected. So follow the same process here. Here, we are trying to do a doping, that is boron doping, ion implant. So here there are two types of mask. One is positive mask and one is negative mask. Here we have selected it as negative mask by selecting this to be in the outside option. Only with this 4 we will see what has been created. Only with the first 4 steps, let's see what has been created. Sequence, next, deposition of PR material, next, it is UV lithography, that is negative masking. Step 4, boron implant. So what is this boron implant is? Basically an impurity that gets added. Let me hide this. You can see that boron gets implanted inside. It is not deposition above. It gets inside that substrate. That's a piezoresistive material. Okay, so I'll disable this. Here, in case if I take this as a positive masking, let's see what happens. I select this and then click inside and save this file, visualize in FabSim. So this is positive masking, and then boron will get deposited all across. Okay, only in this region it will not be there. Okay, so here we are trying to do negative masking, that is we select outside. Further above this we deposit Si3N4, deposition of PR material. We repeat the steps with different materials, deposition, lithography and etching, and then with different deposition methods and with different etching methods, we create multiple geometries. So here deposition of Si3N4 is about 100 micrometer, and then above that we have a PR material. By default it is 300 micrometer. UV contacts us. So this time we are trying to create a via hole. Again you may notice that it is outside edge, and this is a via. So let's see in the visualization. Process number 8. Until 8 we shall go. Sorry, until 9 we shall go. So till here we have seen how this via contacts are there. Okay. And now metallization. So we deposit aluminium, thickness 200 micrometer. So you can change the thickness based on your requirement, and deposition of PR material again. And again we do lithography process with metal layer this time. Okay, and then we etch aluminium, and then we etch silicon nitride, and then we have PR material etching, and finally we deposit PR material again in the bottom side, and then we do the lithography process at the bottom of the device, and then we etch the silicon. So let's see this. I'll go to the last step. The last step is also seen here. You can see that bottom side etching is also done. So if we look at the cross-sectional view, you can see that the device is like this. Okay. Fine. So let me disable this cross-sectional view. Click OK. So this is the process simulation. Okay, once the file is created, once the process simulation file is created, we select this option and then we'll try to push this design to the analysis module. File, give a name to it, and then it gets exported to thermoelectromechanical module. Okay, this is where we have this file. Let's perform the simulation. Let's perform static analysis on this one. So it's a piezo resistive material. Then we click apply. Okay. Material properties, specific values. So here you can change the elastic parameter 130, and this is to be 0.278. Rest other materials will retain as it is. And here we have piezo material that we need to select. So as we select different materials, you can see each entity, the window turns red. So here we go to piezo resistive coefficients, and then we will say table, give the piezo values to be 6.6, E minus 6, minus 1.1, E minus 5, 0.00138, and here we need to also define piezo resistive to the metal layer also. For metal layer, we don't have to define it, but again, when we want to do the electrical analysis, we require these wires. So hence, we will just select table and then we will keep the pi coefficients 0. Okay, and then we click OK. Loads, we go to pressure, phase, above this, select, and then we'll define 0.1 megapascal of pressure, that is 1 bar of pressure. Then go to boundary, fixed, and then we shall fix this bottom surface of the frame. Click OK. When you rotate here, don't rotate it by click on the geometry itself, because that face will get selected. So use the outside area, hold the left button of the mouse, and you can rotate it. Then go to mesh, auto mesh. So as of now, I'll just keep it very coarse, 200 micrometers. So you can do the refinement based on your requirement. And then we go to analysis, and then we do the static analysis. Once the simulation is complete, let's look at the results. Displacement set. Here you can see the maximum displacement is happening in the center. You want to see the animation, go to figure animation, linear motion, click OK. If the displacements are quite significant, then we can see it. So here the displacement is about 0.01 micrometer. So naturally it is very small. It's not visual. So it's not seen. Let me stop this animation. If you want to see it, we can scale it up. Can scale it up by 100 times. So now you can see it. Let me stop this animation. Now it's not just the displacement. One more thing that is most important is the stress distribution. So you can see that stress distribution across the device is seen. Okay. So now based on the requirement, here we perform for various pressure values. In this case, we have done with the mechanical simulation. Let's do the electrical simulation part of it. For this, we go to mesh and then click on extract resistor mesh. So here we had defined piezoresistive material with pi coefficient values. For piezoresistive material, we had defined 0, 0, 0 for pi coefficients of metal layer also. So this is the advantage here. So we can extract even the wire. When we want to do the electrical simulation, even with piezo resistors, even the wire should come in. In case if wire or the metal does not come, then there is no use for electrical simulation. Now we will perform electrical simulation by load, voltage, phase. So here in this portion shall define 5 volts. So on this phase we apply 0 volts. We go to temperature, phase, tell each one of the resistors that you are in room temperature. Let's refine the mesh. Auto, let's go to 10 and then run the static analysis. Go to results, then we'll see the potential. Potential is generated here. Okay, so what we see here is there is a potential on either side. So we applied potential on these 2 points, but we are measuring potential in these 2 points. Okay, shall go to results, node value, click on node value and click on this portion. So we can see that it is 2.49885 volts is generated. On this side it is 0 volts. So 2.49885 volts is seen with pressure of 0.1 megapascal, that is 1 bar of pressure. Okay, now let's repeat the same simulation. So for this we'll have to redo the simulation. Okay, let's redo the simulation. Okay, so I close thermoelectromechanical. I have opened it again. So we open thermoelectromechanical module again and then open this file separately. So since we have saved this file with all the simulation settings, we will anyways have those values. So we'll change this to 0.2. Except that nothing else is a change. Okay, and we'll run the static analysis. Simulation is complete. Let's see the displacement. So displacement has been increased. Now go to mesh, extract resistor mesh, and then we'll repeat same settings again. Voltage phase. So we apply 5 volts, and on this side we apply 0 volt. We go to load, temperature, phase. So each piezo resistors are at 25 degrees. Okay, and once it is done, we go to mesh, auto, 10, click OK, and then we'll redo the simulation. Simulation is complete, and here we see the potential again. Go to results, node value. We see this value, and 0 potential at this point. At this point it is 0. Okay, so this shows that with 0.1 megapascal we generate a different potential, and with 0.2 megapascal we see a different potential. So now if we extract the value of potential for each pressure, then we can take the difference of it, and then we can see that for every pressure there is a change in potential. So now your sensitivity becomes P2 minus P1. Okay, so that's the sensitivity of the pressure sensing device.